Hello everyone, welcome to my channel. Today we'll be learning about hybrid machine learning model for efficient botnet attack detection in IoT environment. The contents of the presentation are introduction, related background, working or implementation, evaluation parameters, results, future enhancements, conclusion, and references. Introduction. Cyber attacks are growing with rapid development and wide use of internet technology. Botnet attack emerged as one of the most harmful attacks. A botnet is a network of compromised computers, often controlled remotely by attackers. Botnet identification is becoming challenging due to the numerous attack vectors and ongoing evaluation of viruses. Botnets pose serious risks to the network security, and deep learning models have shown potential for efficiently identifying botnet attack activity for network traffic data. This research proposes a stacking model ACNR for botnet attack identification to improve security measures for IoT systems. The proposed model utilizes the strengths of artificial neural networks (ANN), convolution neural networks (CNN), long short-term memory (LSTM), and recurrent neural networks (RNN). Network traffic analysis based on deep learning have becoming an effective tool for spotting and reducing botnet activity. These analyzers use deep learning models to automatically extract pertinent information from unprocessed packets of data. The first few packets in a flow's header are specifically extracted and examined to look for patterns and traits typically for botnet traffic. Using convolution neural networks and autoencoder, it is possible to identify malicious activity and which is independent of the architecture of the underlying botnet. Autoencoders are used to teach the network how to put input and learn the fundamental form of network traffic data. Introduction. Bidirectional long short-term memory recurrent neural networks are famous example of how deep learning is being used in botnet identification. These models are well suited for analyzing network traffic and spotting trends connected to botnet activity because excellent they are excellent at collecting both the past and future context of sequential data. There are various benefits to using deep learning algorithms for botnet identification. First of all, these algorithms are capable of learning and adapting automatically to the changing characteristics of botnets, allowing them to recognize novel and previously unknown botnet behaviors. Second, these algorithms can find hidden patterns and anomalies that would not be noticeable using conventional detection techniques by extracting characteristics from raw data packets. By utilizing deep learning algorithms in botnet detection, researchers and practitioners expect to increase the accuracy and efficacy of detection approaches and enable proactive protection strategies against botnet attacks. Related background. Attacker, Attacks can be divided into two categories, passive and active, depending on their nature. The passive attack may be network or system based, with the attacker covertly monitoring the network to obtain private data. Active attackers bypass all security precautions and gain access to networks by taking advantage of security flaws and stealing credentials. Cyber security attacks, that is botnets. Botnets are a collection of hacked computers that are coordinated by a master host and used for malicious purposes like spam distribution, DDoS, and data theft. Traditional botnet detection techniques like anomaly-based identification and signature-based approaches have trouble identifying unknown botnets, encrypted traffic, and complex evasion strategies used by attackers. DDoS attacks, the largest and the most destructive internet cybercrimes, have involved DDoS attacks. The Mirai botnet was also one of the most well-known instances of a DDoS assault using the IoT. A DDoS attack is a cyber attack in which a hacker temporarily subjugates several compromised systems to attack a particular target and send concurrent requests to a server for a specific service, overwhelming the server and convincing it to disregard real requests from the end users. CNN LSTM model. A CNN LSTM model is used for botnet attack detection. IoT setting categorize network activity by observing Wi-Fi connections. CNN layers are utilized to extract features from the input data and is used for detection. This model produces results with a specificity of 93%. Working or implementation. The USNW and the NB15 dataset. The USNW NB15 dataset has been used by researchers and cybersecurity professionals to test intrusion detection systems and create algorithms to find different kinds of network assaults, including those that may harm IoT devices and network. The dataset is configured as a training set and a testing set, namely USNB15 training set.csv file and USNB15 testing set.csv file, respectively. The total number of records in the dataset is 82,332 that contains 9 types of attacks, including normal, generic, exploits, fuzzers, DOS, reconnaissance, analysis, backdoor, shellcode, and worms. Data preprocessing. Preprocessing must be completed before any analysis to make the data ready for the model training and testing. The dataset needs to be loaded, cleaned, modified, and transformed into a form that is appropriate for machine learning models. Artificial neural networks, ANN, and crucial components of deep learning which are motivated by the design and operation of a human brain. ANNs are used in deep learning to conduct complex calculations on vast volumes of data. Convolution neural networks. An advanced form of an ANN is CNN, which is created to be particularly effective at processing and analyzing visual data, such as pictures and movies. CNNs are very good at extracting significant patterns and characteristics from images. The input data is subjugated to filters in the convolution layer, which enables the network to learn regional patterns and spatial hierarchies. The completely connected layers are the network's end are where the high level features are processed and the final output is produced. Long short term memory network. The LSTM algorithm is an example of recurrent neural network RNN architecture created expressly to represent and analyze sequence data. LSTMs can capture long short-term dependencies and maintain information over long periods of time, unlike conventional RNNs. The pertinent information is stored and updated by the memory cells, and the gates decide facts are important and which facts are important to remember and which are not. The three gates that control the information flow via the LSTM unit gates are for input, forgetting, and output. Recurrent neural networks. An artificial neural network that works well for processing sequential data is RNN. RNNs are opposed to conventional feed-forward networks, feature connections between nodes, and create a directed cycle, which enables them to remember information and gain knowledge from prior inputs. RNNs can represent sequences of any length and capture temporal dependencies thanks to the cyclic structure. RNNs are effective for tasks like pre-processing natural language, speech recognition, and handwriting recognition due to their recursive feature. Propose stacking ACLR1. A deep learning technique called stacking is used to integrate the results of various classification models to get a more potent and precise final prediction. To improve the overall predictive performance, stacking combines several models. By stacking models, we can benefit from the strengths and diversity of different algorithms. Each algorithm may have its unique way of capturing the data patterns and linkages, and by combining the predictions, we can make a prediction that is more reliable and precise. Stacking helps in reducing bias and variance, improving generalization to the data. Stacking is Stacking is a powerful assembled learning technique that leverages the strength of multiple deep learning algorithms, including ANN, CNN, LSTM, and RNN. By combining their predictions in a layered fashion, stacking can enhance the overall predictive performance, leading to improved accuracy and robustness in deep learning models. Coming to the evaluation parameters, accuracy, recall, and precision are common measures for assessing the efficacy of machine learning models, particularly for classification tasks. The model's ability to forecast the various classes or categories of the input data is indicated by these measures. The proportion of accurately anticipated positive instances recall, often referred to as sensitivity or the true positive rate, refers to responses to actual positive events. It demonstrates that the model can accurately identify all relevant positive cases. Higher recall values suggest that the model is good at minimizing false negatives. Recall is equal to TP upon TP plus FF. Precision, commonly referred to as positive predicted value, is the ratio of accurately predicted positive cases to all expected positive cases. It demonstrates accuracy in identifying positive samples and in minimizing false positives. Precision is equals to TP upon TP plus FP. High accuracy values simply the model generates minimal false positives. Accuracy is equals to TP plus TN upon TP plus TN plus FP plus FN, where TP stands for true positive, which is the number of packets, the number of correctly predicted attacks. FP stands for false positive, which indicates the number of a normal attack, indicates a normal attack. Evaluation parameters. An often used statistic in research articles to assess the efficacy of classification systems is the F1 score. By including precision and recall into a single score, it provides an accurate evaluation of the model's performance. The following formula used to determine the F1 score. F1 score is equals to 2 into precision plus recall, precision into recall, divided by precision plus recall. The ROC-AUC measure the area under the receiving operating characteristic curve. It's a graphical representation of a binary classification model's performance. It plots the true positive rates against the false positive rates at various thresholds. The ROC-AUC represents the area under the ROC curve and ranges from 0 to 1, where a higher value indicates better model performance. A value of 0.5 indicates suggests a random classification, while a value of 1 indicates perfect classification. The PRAUC measures the area under the precision recall curve, which accesses a model's performance in binary classification with a focus on positive class prediction accuracy. The PRAUC represents the area under the precision recall curve and ranges from 0 to 1, with higher values indicating better model performance. Coming to the results, a selection criteria for deep learning algorithms have been adopted based on less complexity and works better with small datasets instead of large datasets. By using 70% training data and 30% testing data from the dataset, the performance of the deep learning model is accessed. Experimental results demonstrate that the proposed model shows better performance than other deep learning models used in this research, with the highest accuracy score of 0.9698. This accuracy is better than the LSTM model, which has the best accuracy score of 0.9651. The precision, recall, and F1 scores of the proposed model are also highest with 0.9691, 0.9693, and 0.9692 for the period of the training session, respectively. Proposed data-driven solutions use a variety of neural network architectures, including ANN, CNN, LSTM, and RNN. ROC-AUC and PRAUC metrics are used to measure model efficacy, guaranteeing strong classification performance and a thorough comprehension of model behavior. The performance of ROC and PRAUC are shown in the given figures below. The accuracy shows that correctly predicted values over the total number of predictions, which shows how many numbers of attacks have been detected in real-life systems. The proposed ACLR model shows an accuracy of 97.49%, which means approximately 97.50%. Future enhancements involve. It is possible to note that deep learning algorithms for Botnet identification still have limitations such as a lack of label statistics on training and the possibility of hostile attacks. To increase the precision, scalability, and robustness of deep learning-based Botnet detection, more research and development in this area is required. Increasing the number of layers for the deployed models is observed to produce better performance. However, it comes at the cost of increased computational complexity and higher training time. There should be a more training using reinforcement learning, which can be more effective. Coming to the conclusions, this research proposes a hybrid stacking model, ANN plus CNN plus LSTN plus RNN, combining to form the ACLR for botnet detection. The experimental setup involves ACLR implementation in the Google Colab environment using the UNSW NP15 dataset. The performance analysis for existing models indicates that ACLR can perform better than state-of-art models. Evaluation metrics including ROC-AUC and PRAUC have been used to evaluate the performance of the proposed research based on the ACLR. The highest ROC-AUC is 0.9934 and PRAUC is 0.9950, which has been achieved. The comprehensive assessment of parameters encompassing accuracy, precision, recall, and F1 score collectively emphasize the robustness of ACLR in detection and mitigating of botnet threats within IoT environments. These are the references. Thank you for watching the video. If you like the video, please do like, share, and subscribe.